Stand at the shore of an ocean and you can see the horizon, a clean line where water meets sky, where the visible world ends and something unknown begins. But you know what lies beyond that horizon. More ocean, more sky. The same rules, the same physics, just more of what you already know exists. You could board a ship and sail toward that horizon, and as you approached it, you'd see it recede before you, always maintaining the same distance. But eventually, with enough travel, you'd discover new lands, new continents, new horizons beyond the first. The horizon is an illusion created by your limited vantage point, not a real boundary. Now imagine standing at the edge of the universe. What would you see there? What lies beyond the furthest reaches of everything that exists? The answer to this question will unsettle you. It will challenge everything you think you understand about existence, about boundaries, about the very concept of beyond. Because the universe doesn't play by the rules we're used to. It doesn't have an edge in any sense you can imagine. And what might lie beyond our cosmic horizon is stranger than any science fiction writer has ever conceived. For thousands of years, humans have wondered about edges. The edge of the world, the edge of the sky, the edge of reality itself. Ancient civilizations imagined the Earth was flat with literal edges you could fall off. Medieval mapmakers wrote, "Here be dragons," at the boundaries of known territory, acknowledging the mystery of unexplored regions while suggesting that something terrifying might lurk there. The fear of edges, of boundaries, of the unknown beyond seems hardwired into human psychology. We want to know what's out there even as we fear what we might discover. But cosmology has revealed that the universe operates on principles far stranger than falling off edges or encountering dragons. The edge of the universe, if such a thing can even be said to exist, is not a place you can travel to. It's not a wall or a barrier or a boundary in any conventional sense. It's a limit imposed by the fundamental structure of space-time itself, by the speed of light, by the age and expansion of the cosmos. And what lies beyond this limit might be literally everything more space than you can imagine, more galaxies than you can count, possibly more universes than physics can describe. Right now, at this very moment, you exist within a bubble. A sphere of visibility roughly 93 billion light-years across, centered on you. Every photon of light that reaches your eyes, every particle of radiation detected by our most sensitive instruments, comes from within this sphere. Beyond its boundary lies what exactly? More universe? Different universes? Nothing at all? The answers proposed by the modern physics are so extraordinary that they border on the incomprehensible. Scientists have peered deeper into space than ever before, watching galaxies as they appeared billions of years ago, capturing light that has travelled across unfathomable distances to reach our telescopes. But the further we look, the stranger things become. Galaxies rush away from us at velocities that seem to violate the speed of light. Space itself expands faster than light can cross it. And at the very edge of what we can possibly observe, we encounter a wall not made of matter or energy, but of time itself. This is not a story about where the universe ends, this is a story about whether that question even makes sense. About the moment when human curiosity crashed headlong into the fundamental limits of knowledge. About the discovery that the universe might be infinite in extent, or finite but without edges, or just one bubble in an eternal sea of other universes being born every moment. About the realization that reality extends far beyond anything we can ever hope to see or measure or understand. The edge of the universe is the edge of everything we can know, and what lies beyond it may be the most profound mystery our species will ever contemplate. If you're ready to peer over that edge, to glimpse the theories and possibilities that emerge when physics pushes past its own limits, then let's begin this journey together. Because once you understand what modern cosmology says about the universe's boundary, you'll never look at the night sky the same way again. When you look up at the night sky, you're seeing the past. The light from the stars has taken years, decades, sometimes millions of years to reach your eyes. Every photon carries information about the universe as it was, not as it is. The further away an object is, the further back in time you're looking. This simple fact creates one of the most important concepts in cosmology, the observable universe. The observable universe is not the universe. Let me repeat that because it's crucial to everything that follows. The observable universe is simply the portion of the universe from which light has had time to reach us since the Big Bang. It's a sphere centered on Earth, with a radius of approximately 46.5 billion light-years in terms of current proper distance. That gives it a diameter of roughly 93 billion light-years. Everything within this sphere is, in principle, observable to us. Everything beyond it is not. You might be thinking, wait, if the universe is only 13.8 billion years old, how can we see objects that are now 46.5 billion light-years away? Shouldn't the radius be 10.8 billion light-years? This confusion arises from forgetting that the universe has been expanding all this time. When a photon began its journey toward us from a distant galaxy 13 billion years ago, that galaxy was much closer. But during those 10 billion years, space itself has been stretching. The galaxy has been carried away from us by the expansion of space. By the time the photon reaches us, that galaxy is now much further away than the photon travelled. In fact, due to the accelerating expansion driven by dark energy, that galaxy is now approximately 46.5 billion light-years distant. This boundary of the observable universe is called the particle horizon. It represents the maximum distance from which light could have travelled to reach us in the age of the universe. Beyond the particle horizon lies a vast expanse about which we can know nothing. Not because of technological limitations, not because we haven't built powerful enough telescopes, but because of the fundamental structure of spacetime itself. Light from regions beyond the particle horizon has not had enough time to reach us. The signals are on their way, but they haven't arrived yet, and for some regions, as we'll discover, they never will. Think about what this means. Right now, somewhere beyond your cosmic horizon, there might be a galaxy identical to the Milky Way. It might contain a planet identical to Earth, with continents in the same shapes, oceans with the same chemistry, perhaps even cities and civilizations, but you will never see it. No telescope, no matter how powerful, will ever capture its light. Not because the technology doesn't exist, but because the photons haven't had time to cross the intervening space. The universe is only 13.8 billion years old. Light travelling from that distant galaxy has been in transit for billions of years, but it hasn't arrived yet. Maybe it will arrive in another billion years, or 10 billion, or 100 billion. But by that time, other factors come into play. Factors that make the situation far more complicated and disturbing. The particle horizon is not a physical structure. There's no wall there, no membrane, no change in the properties of space itself. If you were somehow instantly teleported to a point at what is currently your particle horizon, you wouldn't notice anything special. Space would look the same as it does here. Galaxies would surround you in all directions, the laws of physics would be identical. The only difference is that Earth would now be at the edge of your new observable universe, appearing to you as we now see objects at our particle horizon young, distant, part of the ancient cosmos. And stretching away from Earth in the opposite direction would be a whole new observable universe worth of galaxies that were previously beyond your horizon. This is a profound point. The observable universe is not the universe. It's your universe, the portion you can see from your particular location in space and time. An observer in a galaxy 10 billion light-years away has their own observable universe, a sphere centered on them, containing galaxies we can never see, and missing some galaxies we can see. The two observable universes overlap but are not identical. Each observer has their own cosmic bubble, their own horizon, their own edge, beyond which lies the unknown. The particle horizon grows larger every day. As the universe ages, light from previously unreachable regions crosses into our observable sphere. New galaxies wink into visibility at the edge of what we can see, having finally sent their ancient photons our way after billions of years of travel. You might imagine that given enough time, we would eventually see the entire universe. That everything would eventually become observable as light from every corner makes its way to us. This intuition is tragically wrong. The expansion of the universe is accelerating. Dark energy, that mysterious force that makes up approximately 68% of all energy in the cosmos, is pushing space apart at an ever-increasing rate. This acceleration creates a second, more disturbing horizon, the cosmic event horizon. Beyond this boundary, approximately 16 billion light-years away in present-day terms, lie regions that are receding from us faster than light can travel through space. Photons emitted from those regions right now will never, ever reach us, no matter how long we wait. Even though those photons travel toward us at the speed of light, the space between us and their source expands faster than they can cross it. They are like someone running up a down escalator, sprinting at maximum speed but still being carried backwards. Let's make this concrete with numbers. Consider a galaxy currently sitting at the cosmic event horizon, 16 billion light years away. A photon leaves that galaxy, heading toward us at the speed of light, travelling at 300,000 kilometers per second. But space between us and that galaxy expands at a rate that depends on distance. At 16 billion light years, spent is expanding at exactly the speed of light. The photon makes progress through space, but space is being added behind it at the same rate. It's running in place. Actually, it's worse than that. As the photon gets further from the source galaxy, it enters regions where space is expanding even faster because the expansion rate increases with distance. The photon starts losing ground. It travels billions of kilometers every second, but trillions of kilometers of new space are created between it and us in that same second. This photon will travel forever, never slowing, never stopping, always moving toward us at light speed. But it will never arrive. In a trillion years, it will be further from Earth than it is now, despite having travelled for a trillion years at the maximum possible speed. The expansion of space has defeated it. This is not a race the photon can win, and this means that galaxy, currently visible to us, is sending us its last photons. The light we see from it now was emitted in the past when the galaxy was closer to us, but any light it emits from this moment forward is already lost, doomed never to reach us, carried away by the accelerating expansion. This means the observable universe is not just limited by the past, it's limited by the future as well. There are galaxies we can see today whose light is reaching us right now, but any light they emit from this moment forward will never reach us. We're watching them in real time, but we're watching their last moments of visibility. Over billions of years, these galaxies will appear to slow down, redden, and fade from view, frozen at the moment when their light could no longer overcome the expansion of space. They'll dim and dim and dim, their light stretched to ever longer wavelengths, until they vanish into infrared, then radio waves, then wavelengths so long that no detector could ever capture them. They'll effectively disappear from the universe as far as we're concerned, not by being destroyed but by receding beyond the reach of light itself. And it's not just distant galaxies. Closer objects will eventually cross this horizon too. The Virgo supercluster, a massive collection of galaxy clusters including our own local group, is gravitationally bound enough to resist the expansion for now, but the more distant galaxy clusters, the ones hundreds of millions of light years away, are already slipping away. In 100 billion years, an observer in the Milky Way will see a much lonelier cosmos. Most of the galaxies visible tonight will have vanished beyond the event horizon, redshifted out of existence. The night sky will be darker, emptier, more isolated. This means the observable universe is not just limited by the past, it's limited by the future as well. There are galaxies we can see today whose light is reaching us right now, but any light they emit from this moment forward will never reach us. We're watching them in real time, but we're watching their last moments of visibility. Over billions of years, these galaxies will appear to slow down, redden, and fade from view, frozen at the moment when their light could no longer overcome the expansion of space. Stand at the edge of the observable universe in your imagination. You're 46.5 billion light years from Earth, somehow instantly transported to this cosmic frontier. What do you see? You see another observable universe, one centered on you. The Milky Way now sits at the edge of your particle horizon, a faint smudge of light showing our galaxy as it appeared 46.5 billion years ago. In every direction around you, you'd see galaxies and structures remarkably similar to what we see from Earth. Because the universe on the largest scales appears to be uniform, homogeneous, the same in all directions. This uniformity is both beautiful and puzzling. It's beautiful because it suggests that Earth is not special, or we don't occupy some unique position in the cosmos. The view from here is probably very similar to the view from anywhere else, but it's puzzling because it raises a question that haunts cosmology. If the observable universe is just a small bubble in a much larger space, and that larger space is uniform and similar to what we see, then how large is the total universe? Does it extend infinitely, or does it curve back on itself somehow? Is there an edge out there somewhere, or does space simply go on forever? The observable universe contains approximately 2 trillion galaxies. Each of those galaxies contains hundreds of billions to trillions of stars. Most of those stars likely have planets. The sheer number of worlds within our cosmic bubble is incomprehensible. Yet this entire mind-boggling collection of galaxies and stars might represent only an infinitesimal fraction of what exists. If the universe is infinite, then the observable universe is literally 0% of the total. We can see nothing at all, statistically speaking, of what's actually out there. This creates a profound limitation on human knowledge. We can only ever observe a finite portion of reality. Our particle horizon grows. Yes, but the cosmic event horizon ensures that vast regions will slip away from us forever, pushed beyond observation by the accelerating expansion. We live in an expanding bubble of visibility, surrounded by an infinite darkness we can never penetrate. And what lies in that darkness? That's where the theories begin. That's where physics stops giving us certain answers and starts offering possibilities instead. But before we explore those possibilities, we need to understand something even stranger about our cosmic boundary. The edge of the observable universe is not just something we can't reach. It's something that moves away from us the harder we try to approach it. It's a horizon that recedes before us, always staying the same distance ahead, no matter how fast we travel. Let's understand why. Imagine you've built a spaceship capable of traveling at the speed of light. The ultimate vehicle, pushing the limits of physics, crossing space at 300,000 kilometers every single second. You point your ship at the edge of the observable universe and accelerate to maximum velocity. How long would it take you to reach the boundary, to cross that cosmic horizon and see what lies beyond? The answer: you would never reach it. Not in a billion years, not in a trillion, never. This isn't a problem of insufficient speed. Even at the speed of light, the fastest velocity possible in our universe, you cannot reach the particle horizon. The reason why reveals something profound about the nature of space itself. As your light-speed spacecraft hurtles through space, heading toward what is currently the edge of your observable universe, that edge is moving away from you. Not because there's something at the edge running away, but because the space between you and that distant point is expanding. Every second, new space is created between you and your destination, and the further away your destination is, the faster new space appears between you and it. Here's where it gets truly mind-bending. The expansion rate of space is described by the Hubble constant, currently measured at approximately 7 to 73 kilometers per second per megaparsec, depending on the measurement method used. A megaparsec is about 3.26 million light-years. This means that for every 3.26 million light-years of distance, space expands by roughly 7 to 73 kilometers every second based on current observations. An object 3.26 million light-years away is receding from us at about 70 kilometers per second on average. An object 32.6 million light-years away is receding at around 700 kilometers per second. An object 3.26 billion light-years away is receding at roughly 70,000 kilometers per second. Do the math far enough and you'll find that objects beyond a certain distance are receding from us faster than the speed of light. At the particle horizon, approximately 46.5 billion light-years away, the recession velocity is vastly superluminal. Space expands there at many times the speed of light. Wait, you might think. Doesn't Einstein's theory say nothing can move faster than light? It does, but there's a loophole. Objects cannot move through space faster than light, but space itself can expand at any rate whatsoever. The speed limit applies to motion through space, not to the expansion of space itself. Galaxies at the edge of the observable universe aren't moving through space faster than light. They are being carried along by space that's expanding faster than light can cross it. Now imagine your journey again. You're racing toward the edge at light speed, but the edge is receding from you at much more than light speed. With every second that passes, the distance between you and the particle horizon increases. You're running as fast as physics allows, and the goal is moving away faster than you're running. The gap widens. The journey becomes longer, not shorter. But surely you might think, after enough time, the expansion will carry you far enough from Earth that new galaxies will come into view. Your own observable universe will expand, revealing new cosmic territory. This is true. Your particle horizon does grow, but it grows in all directions, including the direction you came from. Earth slips away behind you, approaching your rear particle horizon. You're not reaching the edge of the universe, you're simply changing your position within an infinite ocean, with your bubble of visibility moving with you wherever you go. The edge remains always the same distance ahead. The situation is even worse when we consider the cosmic event horizon. This boundary, sitting at approximately 16 billion light-years in current proper distance, represents a more absolute limit. Beyond this event horizon are regions of space that are receding from us at exactly the speed of light or faster. Any signal emitted from those regions right now will never reach us, even given infinite time. The expansion of space will always outpace the signal's progress toward us. Think of it like this: you're on a treadmill that's accelerating. You run forward at your maximum sustainable pace, but the treadmill speeds up. Eventually, it's moving backward faster than you can run forward. You maintain your maximum forward speed, expending all your energy to run as fast as possible, but you're actually moving backward relative to the ground. The starting point gets further and further away despite your desperate sprint. Replace you with a photon and the treadmill with expanding space, and you have the situation for signals trying to reach us from beyond the cosmic event horizon. This event horizon is shrinking in co-moving coordinates, even as the particle horizon expands. Galaxies we can see today are slipping beyond the event horizon. We can still see them as they were, because the light from their past has already reached us. But light they emit now, today, will never arrive. They're crossing a point of no return, slipping away into permanent unobservability. In a very real sense, they're leaving our universe, not going anywhere, not moving to another dimension, just receding so far and so fast that they exit our sphere of causality forever. The accelerating expansion driven by dark energy makes this worse. As billions of years pass, more and more galaxies will cross the event horizon. The observable universe will actually shrink in terms of the number of observable galaxies, even as the particle horizon technically expands. Far in the future, perhaps 1 trillion years from now, an observer in the Milky Way would see a much emptier cosmos. Most galaxies will have redshifted beyond visibility, their light stretched to such long wavelengths that no detector could capture it. The observable universe will contain only the local group of galaxies bound together by gravity, surrounded by darkness. This creates a scenario even more claustrophobic than our current situation. Future observers, if any exist, might develop cosmology and astronomy and look out at their sky and see only the Milky Way and Andromeda, and a handful of satellite galaxies. No distant galaxies, no cosmic microwave background radiation. It would have been redshifted beyond detection. They would have no evidence for the Big Bang, no way to measure the expansion of the universe. No indication that 99.9% of the galaxies that once existed are still out there, just beyond reach, hidden by the expansion of space. Those future cosmologists might conclude they live in a static universe containing only a few dozen galaxies surrounded by infinite empty space. They would be completely wrong, but they would have no way to discover their error. The evidence would be hidden behind a horizon imposed by physics itself. This is the ultimate limit of knowledge, not technology, not intelligence, but the structure of space-time itself, which draws a curtain around us that can never be pulled back. So we return to the question, what lies beyond the edge, beyond the particle horizon, beyond the event horizon? We cannot observe it, we cannot reach it, we cannot receive any signals from it. In the strictest sense, it might be meaningless to ask what's there, because there is permanently disconnected from us. It cannot affect us. We cannot affect it. For all practical purposes, it doesn't exist in our universe. And yet physics gives us ways to think about it. Cosmological models make predictions that extend far beyond what we can observe. Mathematics carries us past the horizon into territories no telescope will ever reach, and those predictions are staggering. They suggest that the observable universe, vast beyond comprehension, might be the tiniest speck in something far grander. Let's explore those predictions. The universe has a shape, not in the sense that it looks like a sphere or a cube, or any three-dimensional form you can visualize, but in the sense that the geometry of space itself has properties that can be measured, classified, and described mathematically, and that geometry determines whether the universe is infinite or finite, whether it has edges or not, whether you could, in principle, travel in a straight line and eventually return to your starting point. This is where things get conceptually challenging, because we're talking about the shape of space itself, not objects in space. Space. the medium in which everything exists. To understand what this means, we need to think about dimensions. You live in 3 spatial dimensions: up, down, left, right, forward, backward. These 3 perpendicular directions define our everyday experience of space. Now imagine a creature living in only 2 dimensions, a truly flat being existing on a surface, unable to perceive or move in the 3rd dimension. For this creature, its entire universe is a 2-dimensional surface. That surface could have different geometries. It could be a flat plane extending infinitely in all directions. Euclidean geometry would apply. Parallel lines never meet. The angles of a triangle sum to exactly 90 degrees. Travel in any direction forever, and you never return to your starting point, because the surface is infinite. Or the surface could be curved. Imagine the surface of a sphere, like Earth. It's a 2-dimensional surface curved through 3-dimensional space. For our flat creature living on this surface, something strange happens. If it starts at the equator and travels in what it perceives as a straight line, it will eventually circle the globe and return to its starting point. The surface is finite, but it has no edges. There's no boundary where the surface stops. You can travel forever and never reach a limit, yet the total area is finite. The geometry on a sphere is different from flat geometry. Parallel lines, if extended far enough, eventually converge. The angles of a triangle sum to more than 180 degrees. A triangle drawn from the North Pole down to the equator, along the equator for a quarter of Earth's circumference, and back up to the North Pole, has 3 90-degree angles. That's 270 degrees, not 180. This is positive curvature. Or imagine a saddle-shaped surface. This has negative curvature. Parallel lines diverge. The angles of a triangle sum to less than 180 degrees. This surface could extend infinitely in all directions, or it could close back on itself in complex ways that are hard to visualize. Now take these concepts and add a dimension. Our universe is a 3-dimensional space that could have curvature in a 4th spatial dimension we cannot directly perceive. Just as a 2-dimensional sphere is a curved surface in 3-dimensional space, our 3-dimensional universe could be curved in a 4-dimensional space. The curvature of the universe is determined by its density. Einstein's equations of general relativity connect the curvature of space to the amount of mass and energy it contains. There's a critical density calculated to be approximately 9.5 times 10 to the power of negative 27 kilograms per cubic meter based on current measurements, which determines whether space is flat, positively curved, or negatively curved. If the actual density of the universe exactly equals the critical density, space is flat, like an infinite plane. If the density exceeds the critical value, space has positive curvature, like the surface of a sphere. If the density is less than critical, space has negative curvature, like a saddle. For decades, cosmologists tried to measure the curvature of the universe. They looked at the temperature fluctuations in the cosmic microwave background radiation, using the patterns there to determine the geometry of space. They studied the distribution of galaxies, using their clustering to infer curvature. They measured how light from distant supernovae appears to us, using the relationship between distance and brightness to constrain the geometry. How do you measure the curvature of space? You can't exactly take a ruler to it. Instead, cosmologists use several clever methods, each exploiting different physical phenomena to probe the geometry of the cosmos. One method involves examining the cosmic microwave background, that ancient light from when the universe was only 380,000 years old. In the early universe, sound waves rippled through the hot plasma, creating regions of compression and rarefaction. When the universe cooled enough for atoms to form, those sound waves froze into the pattern of density variations we see today. The physical size of these variations was determined by how far sound could travel in 380,000 years, a calculable distance of about 500,000 light years. But the apparent size of these variations, as seen in the cosmic microwave background, depends on the geometry of space. In a flat universe, a structure 100,000 light years across at a known distance will subtend a specific angle on the sky. In a positively curved universe, like looking through a cosmic magnifying glass, that same structure will appear larger. In a negatively curved universe, it will appear smaller. By carefully measuring the angles subtended by these acoustic peaks in the cosmic microwave background, cosmologists can determine whether space is flat, positively curved, or negatively curved. The Wilkinson Microwave Anisotropy Probe and later the Planck satellite made these measurements with extraordinary precision. They mapped the temperature variations in the cosmic microwave background to millionths of a degree across the entire sky, creating detailed statistical analyses of the patterns. The result? The universe is flat to within 0.4%. The measured curvature is consistent with zero. Space, on the larger scales, appears to be Euclidean. Another method involves Type 1a supernovae, stellar explosions that reach a predictable peak brightness. These standard candles allow astronomers to measure cosmic distances. In a curved universe, the relationship between distance and apparent brightness would differ from a flat universe. The curvature would cause light to bend and focus, making distant supernovae appear brighter or dimmer than they would in flat space. Extensive surveys of distant supernovae, the same surveys that discovered dark energy, also constrain the curvature of space. They too find it to be flat. A third method examines the large-scale distribution of galaxies. In a curved universe, the clustering patterns would be distorted compared to a flat universe. The universe would act as a lens, warping our view of how matter is distributed. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, measuring their positions in 3 dimensions. The statistical patterns in this cosmic web galaxies clustering, the sizes of voids, the shapes of filaments all depend on geometry, and they all point to flatness. The results? The universe appears to be flat. To within a fraction of a percent, the measured density equals the critical density. The angles of cosmic triangles sum to 180 degrees. Space, on the larger scales, is Euclidean. This finding came as something of a surprise because there is no obvious reason why the density should be so precisely balanced at the critical value. It's like finding a pencil balanced on its tip. Technically possible, but remarkably unlikely unless something is holding it there. That something is probably cosmic inflation, which we'll discuss later. But there's a subtlety here that's easy to miss. Flatness doesn't uniquely determine infinity. The measurements tell us about local geometry, how space curves in our cosmic neighbourhood. But they don't directly tell us about global topology, how space connects to itself on the largest scales. Think about the surface of a cylinder. Locally it's flat. Draw a small triangle on a cylinder, and its angles sum to exactly 180 degrees. Parallel lines stay parallel. All the tests for flatness give you flat results. But globally, the cylinder has an interesting property. If you travel far enough in one direction, you loop back to where you started. The surface is finite, even though it's locally flat. The same could be true for our 3-dimensional universe. Space could be locally flat everywhere, passing all our curvature tests, while still being finite through some exotic topology. Imagine a 3-dimensional version of a torus, or a cube where opposite faces connect, or any number of even stranger shapes. These spaces are flat locally, but finite globally. You could travel in what you think is a straight line and eventually return to your starting point, having circumnavigated the universe. If the universe is flat, does that mean it's infinite? Here's where topology enters the picture. Topology is the study of properties that remain unchanged when you stretch or bend space without tearing it. A cylinder and a plane have the same local geometry. Both are flat, but they have different topologies. On a plane, you can travel forever in any direction without returning. On a cylinder, you can travel forever in one direction, but if you go in the direction around the cylinder, you eventually return to your starting point. A flat space can be infinite, like an endless plane. Or it can be finite, like a 3-dimensional version of a torus or donut. Imagine a cube where opposite faces are connected. Walk out the right side and you reappear on the left. Walk out the top and you reappear on the bottom. This is a flat space. You can verify that triangles have 80-degree angles, but it's finite. If you travel far enough in any direction, you return to your starting point. The universe could be structured this way, a finite flat space wrapped back on itself in strange ways. Cosmologists have searched for evidence of such topology. If the universe were a 3-dimensional torus smaller than the observable universe, we would see multiple images of the same galaxy in different directions. Light from that galaxy would take different paths around the cosmic torus to reach us, creating a hall of mirrors effect. Extensive searches of the cosmic microwave background and galaxy distributions have found no such repetition. Either the universe is simply connected, meaning it's infinite and doesn't wrap around, or any such wraparound occurs on scales much larger than the observable universe, making it impossible to detect. Current best evidence suggests the universe is flat and simply connected. An infinite Euclidean space extending forever in all directions, the observable universe is a finite bubble within this infinite expanse. Beyond the edges of what we can see lies more of the same, more galaxies, more stars, more planets, the same laws of physics, the same fundamental constants, just more forever. But here's the problem. If the universe is infinite, then it contains infinite galaxies, infinite stars, infinite planets. The implications are staggering. In an infinite universe, every possible arrangement of matter that can occur will occur, not just once, infinitely many times. This leads to a counterintuitive consequence. There could be, somewhere in the infinite expanse beyond our observable horizon, regions with arrangements of matter similar or even identical to Earth. Some cosmologists have explored what this might mean for duplicates down to every atom, though this remains highly speculative and depends on assumptions about how matter is distributed across infinite space. This follows from basic probability and infinity, at least in principle. In a finite, observable universe of 93 billion light-years diameter, there are only so many ways you can arrange atoms. The number is incomprehensibly large, but it's finite. Estimates suggest perhaps 10 to the power of 10 to the power of 118 possible quantum states in a Hubble volume. But infinity is bigger than any finite number, no matter how large. So in a truly infinite space with a finite number of possible distinguishable arrangements, some theoretical models suggest arrangements would have to repeat, assuming matter is distributed relatively uniformly on the largest scales. Let's think about this more carefully. Consider a volume of space the size of the observable universe, roughly 4 times 10 to the power of 80 cubic meters. How many different ways could you arrange all the particles in that volume? Each particle could be in one position or another, in one quantum state or another. The number of possible configurations is finite because the number of distinguishable quantum states in a finite volume is finite, according to quantum mechanics. Quantum mechanics limits how finely you can specify position and momentum. Below the Planck scale, around 10 to the power of negative 35 meters, the very notion of position becomes fuzzy. Some theoretical estimates place the number of possible configurations in a Hubble volume at around 10 to the power of 10 to the power of 118, though this calculation involves many assumptions. The vast majority of these configurations would be random arrangements of particles, undistinguished and chaotic. But some configurations would be interesting. Some would contain galaxies and stars. A smaller subset would contain planets. A smaller subset still would contain life. And an even tinier fraction would produce civilizations, technologies, observers. In principle, if the universe is truly infinite, even this infinitesimal fraction of configurations could appear multiple times. Every possible arrangement, no matter how improbable, might occur at vast distances, including arrangements similar to what we observe here, though whether exact atomic duplicates exist remains a matter of theoretical debate among cosmologists. How far away might such similar regions be? The calculation depends on the number of possible arrangements within a Hubble volume. Some theoretical estimates suggest similar regions might exist perhaps 10 to the power of 10 to the power of 28 meters away, though this number carries enormous uncertainty and depends heavily on assumptions about quantum states and matter distribution. That's a distance so large that trying to conceptualize it is futile. To put this in perspective, the observable universe is about 10 to the power of 26 meters across. This hypothetical distance would be incomprehensibly larger still. If we accept the premise of a truly infinite universe with finite possible states, then this logic suggests there could be numerous regions with similar configurations scattered throughout the endless cosmos. Though whether you, in any meaningful sense, exists elsewhere is a philosophical question as much as a physical one. Some theoretical physicists have explored these implications. Regions with similar atomic arrangements might exist infinitely many times across infinite space, though separated by incomprehensible distances. Some of those regions might have arrangements similar to yours up to this moment, with divergences occurring due to quantum randomness. Some might differ in small ways, others in large ways. These variations, if they exist, would be scattered throughout an endless cosmos, completely isolated from one another. The implications extend beyond just potential duplicates of observers. In an infinite universe, this reasoning suggests every possible history might play out somewhere. Every decision point could branch into all possible outcomes, with each outcome potentially realized in some region of the infinite space. That career you didn't pursue might be pursued by a similar arrangement of matter elsewhere. That relationship that didn't work out might work out in another region, assuming such regions exist. Every tragedy and every triumph, every joy and every sorrow, every path taken and not taken, all of them could be playing out across the infinite expanse, or if the universe is indeed infinite and matter is distributed in the way these models assume. This raises profound questions about identity and meaning. If there are infinite copies of you, are you still unique? Does your individual existence matter? Philosophers have struggled with these questions. Some argue that your uniqueness lies not in the configuration of your atoms, but in your specific causal history, your relationships, your experiences. The copies of you in distant regions share your atomic structure but not your history. They're not you in any meaningful sense. Others argue that in an infinite universe, individuality becomes less meaningful, replaced by a statistical distribution of experiences across infinite copies. There's also the Boltzmann brain problem, a thought experiment in cosmology and philosophy. The idea suggests that in an infinite universe with random quantum fluctuations, it might be statistically more probable for a conscious brain to spontaneously form from random particle collisions than for an entire ordered universe like ours to exist and produce brains through conventional evolution. These hypothetical Boltzmann brains would be disembodied consciousnesses with false memories, existing briefly before dissolving back into chaos. If this reasoning holds, an infinite universe could contain vastly more Boltzmann brains than real brains evolved through normal processes. This seems absurd, leading some physicists to suggest either that the universe isn't truly infinite in the right way, or that our understanding of probability in infinite context needs refinement, or that there's something fundamentally wrong with these extrapolations. The Boltzmann brain paradox remains an active area of discussion in theoretical cosmology. This is called the level 1 multiverse in some classification schemes. It's not multiple universes in separate spaces. It's one infinite space containing infinite regions that can never communicate with each other because they're beyond each other's particle horizons. Each of these regions is a universe unto itself from the perspective of observers within it. The implications are profound and disturbing. If the universe is infinite, then every possible history unfolds somewhere. Every decision you could have made, you did make somewhere else. Every career path you could have followed, you are following in another region of the infinite expanse. Death and birth are just local phenomena, the patterns that make you up reassemble infinitely many times across the infinite space. But we should be careful. The infinity of space doesn't necessarily mean infinite matter. It's possible for space to be infinite, but for the number of galaxies to be finite. If the density of matter drops to zero at large enough distances, or space might be infinite in extent, but with a finite amount of stuff spread infinitely thin. These scenarios avoid some of the weird implications of true infinite matter distributions. The question of the universe's geometry remains one of the most fundamental in cosmology. Is space truly flat and infinite? Or does it curve back on itself in ways we haven't detected? The answer determines not just the size of the universe, but the very nature of existence. A finite, closed universe is conceptually different from an infinite, open one. In a finite universe, the sum total of all matter and energy is a finite number. You could, in principle, count every atom, though the number would be ludicrously large. In an infinite universe, Bayesian accounting is impossible. The total matter and energy is infinite, uncountable, unfathomable. Current observations favour the infinite scenario, but observations are limited to our cosmic bubble. What lies beyond could be utterly different, operating under principles we haven't imagined. Which brings us to the next possibility. Perhaps our observable universe isn't just a bubble in infinite flat space. Perhaps it's a bubble in a different sense. A bubble of inflated space, one of countless such bubbles, separated from other bubbles by regions of still inflating space-time. Let's explore this idea. The universe is not expanding because something exploded and sent matter flying outward into empty space. That's a common misconception. The universe is expanding because space itself is growing. Every point in space is moving away from every other point, not because they're traveling through space, but because the space between them is increasing. In the 1980s, physicists realized something extraordinary. the expansion of space can be driven by the energy of space itself, specifically by something called the inflaton field, a hypothetical quantum field whose energy density can cause space to expand exponentially fast. During a period called cosmic inflation, lasting perhaps 10 to the power of negative 35 seconds, the universe expanded by a factor of at least 10 to the power of 26. A region smaller than a proton grew larger than a galaxy. Space stretched so rapidly that the expansion velocity exceeded the speed of light by ludicrous factors. This inflationary epoch solved several problems in cosmology. It explained why the universe is so flat. The rapid expansion stretched any initial curvature away to unmeasurability. It explained why the universe looks the same in all directions. Regions that were once close enough to equilibrate were stretched so far apart that they're now beyond each other's horizons. It explained why we don't see certain exotic particles that should have been created in the Big Bang. The expansion diluted them to undetectable densities. But inflation creates a new mystery, one that might be even more profound than the problems it solved. Once inflation starts, it doesn't want to stop, or rather, it stops in some regions but continues in others, creating a multiverse of bubble universes inflating eternally within a larger inflating background. Here's how it works. During inflation, the inflaton field has high energy. This high energy state is unstable, like a ball perched on a hill. Eventually the field will decay to a lower energy state, like the ball rolling down to the valley. When the inflaton field decays, inflation ends in that region. The energy of the field converts into matter and radiation, heating the region to extreme temperatures. This is the hot Big Bang, the beginning of normal cosmic expansion. This is what happened in our observable universe some 13.8 billion years ago. But here's the key insight. Inflation doesn't end everywhere at once. Quantum fluctuations make the inflaton field vary from place to place. In some regions, the field decays quickly, ending inflation and producing a hot Big Bang. These regions become bubble universes, expanding but no longer inflating. In other regions, the field remains high, and inflation continues. Those regions keep expanding exponentially. Let's put some numbers to this. During inflation, space expands at an exponential rate. Models suggest the scale factor of the universe could double in incredibly brief intervals, perhaps around 10 to the power of negative 37 seconds or less, depending on the specific model. In a tiny fraction of a second, a region smaller than a proton could become larger than what would eventually grow into the observable universe. This represents exponential growth at its most extreme, though the exact numbers depend on the details of the inflationary model being considered. Space doesn't just expand during inflation. According to these models, it explodes outward at a rate that makes even the fastest conventional expansion look stationary. When inflation ends in a region, that region transitions to normal expansion. Space still grows, but at a much slower rate, governed by the matter and energy content of that region and the acceleration from dark energy. Our observable universe has been expanding for 13.8 billion years since inflation ended here, and it's grown to 93 billion light-years in diameter. That's substantial growth, but it's modest compared to inflation. During inflation, depending on the model, space could grow by a factor of at least 10 to the power of 26 in a fraction of a second, with many models suggesting even larger factors. If inflation continued just a bit longer, the factor could reach 10 to the power of 60 or higher. Regions that were once microscopic could become vastly larger than our entire observable universe, according to these theoretical models. Now comes the eternal part. The inflating regions expand so fast that they grow faster than the decaying regions can fill them. Imagine bubbles forming in a pot of boiling water. Each bubble is a universe that has stopped inflating, a pocket of space filled with galaxies and stars. But the water around the bubbles is still inflating, expanding exponentially. New bubbles form within the inflating background. The process never ends. It cannot end. The inflating space always grows faster than the non-inflating bubbles can consume it. Here's why this happens mathematically in these models. Suppose inflation doubles space every 10 to the power of negative 37 seconds in a given model. In any given region, there's some probability that the inflaton field will decay in that time interval. Most regions keep inflating in this scenario, only a fraction stop, but the inflating regions double in volume. So even though some regions stop, the total volume of inflating space increases in the model. After another 10 to the power of negative 37 seconds, space has doubled again, and again a fraction stops inflating. But the exponential growth of the inflating regions always outpaces the decay in these theoretical frameworks. The total volume of inflating space grows without bound, even as individual bubbles constantly stop inflating and form new universes. This is eternal inflation, and it produces a staggering picture of reality. Our observable universe, that 93 billion light-year sphere of galaxies and stars, is just one small region within a much larger bubble of space that stopped inflating 13.8 billion years ago. That bubble might be far larger than our observable region, perhaps hundreds of billions or trillions of light years across, maybe infinite. And this bubble sits within a background of eternally inflating space, separated from other bubbles by regions that are still inflating at exponential rates. Those other bubbles are other universes, completely separate from ours. The space between us and them is expanding so fast that no signal can ever cross it. Light, leaving our bubble, and trying to reach another bubble, would have to traverse the inflating region between them. But that region expands faster than light speed. Much, much faster. The distance grows by factors of 10 to the power of 26 every fraction of a second. No signal, no matter how fast, can make progress through such expansion. We are causally disconnected. Anything happening in those other bubbles cannot affect us, and we cannot affect them. For all intents and purposes, they're in a different universe. The boundaries between these bubble universes are collision walls, places where two bubbles have nucleated close enough that their boundaries eventually meet as they expand. When bubbles collide, the collision releases enormous energy, potentially creating unusual patterns in the cosmic microwave background of each bubble. Some cosmologists have searched for signs of bubble collisions in our cosmic microwave background, looking for circular patterns that would indicate a neighbouring universe once bumped into ours. No definitive detections have been made, but the searches continue. But the story gets stranger. When the inflating field decays, the exact details of how it decays can vary. The different regions might end inflation in slightly different ways, and those differences could translate into different physical properties, different values for fundamental constants, different particles and forces, different laws of physics. In our universe, the electron has a certain mass, the speed of light has a certain value, the strength of electromagnetism and gravity have certain ratios. But in another bubble universe, born from a different decay of the inflating field, these values might be different. The electron could be heavier or lighter. The speed of light might be faster or slower, assuming the structure of space-time itself allows such variation. Electromagnetism might dominate over gravity, or vice versa. String theory suggests there could be a vast landscape of possible low-energy physics, with estimates ranging widely. Some suggesting perhaps 10 to the power of 500 different possibilities, though this number remains highly uncertain and debated. Each bubble universe could, according to some models, randomly end up with one of these possibilities. Most would be sterile, unable to form stars or chemistry or life. But some small fraction might have conditions suitable for complexity, for galaxies and stars, for planets and life, for observers who can wonder why their universe has the properties it does. This is where the anthropic principle enters. If there are countless bubble universes with random physical properties, we necessarily find ourselves in one capable of producing observers, not because our universe is special or finely tuned, but because only in universes with these properties can anyone exist to ask the question. It's a selection effect. We couldn't observe a universe that cannot produce observers. The eternal inflation multiverse is not a fringe idea. It's a natural consequence of the best models we have for inflation. Alan Guth, one of inflation's pioneers, has said that it's hard to build models of inflation that don't lead to eternal inflation. The mathematics seems to demand it. Once inflation starts, quantum effects ensure it continues in some regions forever. The multiverse isn't an optional add-on, it's the generic prediction. But this multiverse is forever beyond observation. The other bubbles are separated from us by eternally inflating space. We cannot see them, we cannot visit them, we cannot detect them directly. This raises a troubling question for science. How do we test a theory that makes predictions about things we can never observe? Some physicists argue that we can't, that eternal inflation and the multiverse are metaphysics, not physics, that science deals with observable, testable predictions, and anything else is philosophical speculation, no matter how well motivated by theory. Others argue that indirect tests are possible. If eternal inflation is correct, it should make predictions about subtle features of our observable universe, the patterns in the cosmic microwave background, for instance, or the probability distributions of physical constants. Testing those predictions tests the theory, even if we can never see the other bubbles. The debate continues, but the mathematical logic is hard to escape. If inflation happened, which seems very likely based on observations, and if inflation is driven by quantum fields, which seems necessary, then eternal inflation is probably happening. Space is probably filled with an infinite number of bubble universes, constantly being born, expanding, evolving. Our entire observable universe, vast and ancient beyond comprehension, is just one bubble among infinite others. And beyond the edge of our bubble, in the inflating space that surrounds it, conditions are so extreme, so utterly unlike anything we experience, that our physics breaks down. If you could somehow cross the boundary of our bubble into the inflating space beyond, you would be torn apart by the expansion faster than your thoughts could process it. The space between your atoms would expand at exponential rates, shredding your body into fundamental particles which would themselves be diluted to emptiness by the runaway growth of space. The edge of our bubble is not a gentle boundary. It's a transition between two radically different regimes of physics, one where space expands slowly, measurably, where galaxies and stars can exist, and one where space explodes outward at rates that dwarf anything in our experience, where matter cannot cohere, where time itself has a different character. Is this what lies beyond the edge of the universe? Other bubbles, other universes, separated from us by an eternally inflating multiverse? The mathematics suggests yes, but there's another possibility, even stranger. One where the multiverse isn't out there in some inflating space, but right here, layered on top of this universe, invisible and inaccessible, yet just as real. Let's explore that possibility. Every moment you make choices, turn left or right, speak or stay silent. Each choice creates a branching point, a junction where history splits into different paths. Normally, we think only one path is real, the one you actually take. The other possibilities evaporate, never to exist. But what if that's wrong? What if every possibility is real? What if the universe splits at every quantum decision point, creating parallel realities where every outcome occurs? This is the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in Talk 57. It's one of the most controversial and philosophically radical ideas in modern physics, and it suggests that beyond the edge of our observable universe might lie not just more space, but other versions of reality itself. Layered on top of this one, inaccessible yet undeniably present. Quantum mechanics is the physics of the very small, describing how particles behave at atomic and subatomic scales. It's a strange theory, one that has resisted human intuition for a century. In quantum mechanics, particles don't have definite properties until they're measured. An electron doesn't have a specific position or momentum until you check. Before measurement, it exists in a superposition of all possible states simultaneously. This creates a problem called the measurement problem. When you measure a quantum system, the superposition collapses into a single definite outcome. The electron is found in one position with one momentum. All the other possibilities vanish. But why? What makes measurement special? What exactly counts as a measurement? These questions have plagued quantum theory from the beginning. The Copenhagen interpretation, developed by Niels Bohr and others in the 1920s, simply asserts that measurement causes collapse. The wave function describing all possibilities reduces to a single actuality when observed. But this raises deep question. What counts as an observer? Does it have to be conscious? Can a machine observe something? What about an animal? Where exactly is the line between quantum and classical? The Copenhagen interpretation doesn't provide satisfying answers. It just says collapse happens when measurement occurs, without explaining why or how. The many worlds interpretation offers a radical solution. Nothing collapses. Every possible outcome of every quantum interaction actually happens. When you measure an electron's position, the universe splits. In one branch you find the electron here, In another branch, you find it there. Both branches are real. Both exist. They just can't interact with each other anymore. They've become parallel worlds. Let's trace through an example in detail. Consider a single atom that might decay radioactively. Quantum mechanics says the atom exists in a superposition of decayed and not decayed until you check. In the Copenhagen interpretation, checking causes the wave function to collapse into one outcome or the other. In many worlds, checking causes the universe to split. The atom decays in one branch, creating a universe where you observe decay. The atom doesn't decay in another branch, creating a universe where you observe no decay. Both outcomes are real. Both use exist in separate branches that can no longer communicate. This splitting happens constantly, everywhere, at every quantum interaction. A single photon encountering a piece of glass either passes through or reflects. In many worlds, both outcomes occur. The universe splits into two branches, one where the photon transmitted, one where it reflected. And since quantum interactions are happening constantly everywhere, trillions upon trillions of times per second, the universe is splitting into unimaginable numbers of parallel branches every instant. Think about what this means for something as simple as a beam of light passing through a piece of glass. Every photon in that beam encounters countless atoms in the glass. Each encounter is a quantum interaction with multiple possible outcomes. In the many worlds interpretation, each possible outcome occurs, creating a new branch. A beam with a trillion photons, each undergoing millions of quantum interactions, could create an incomprehensible number of branches in a microsecond, according to this interpretation. The number of branches in this framework would grow not linearly or exponentially, but super exponentially, far faster than any normal exponential process, though calculating exact numbers involves assumptions about quantum decoherence and what constitutes a distinct branch. Each branch is a complete universe. It has galaxies, stars, planets, people. In some branches, you're reading this sentence. In others, you pause to think. In others still, you never encountered this text at all because some quantum event in your past went differently, leading you down a different path. A quantum fluctuation in a neuron in your brain 5 minutes ago could have made you decide to do something else instead of reading this. In those branches, you're living a slightly different moment, unaware that in this branch you made a different choice. The branching is deterministic. Every possibility that can occur does occur, but from within any single branch, it looks random because you only experience one outcome. When you roll a die, you see one number come up. It feels random. But in many worlds, all 6 numbers came up in 6 different branches. Your consciousness follows one branch, experiencing that specific outcome with no awareness of the other 5 branches where other versions of you saw different numbers. This solves the measurement problem elegantly. There's no mysterious collapse. The universe simply evolves according to the deterministic equations of quantum mechanics, creating a vast branching tree of parallel realities. Measurement isn't special, it's just another quantum interaction that creates branches. The appearance of randomness comes from your subjective experience of being in one branch, unaware of the others. But it comes at a staggering ontological cost. The number of parallel worlds is not just large, it's unfathomably vast, probably infinite. Every quantum interaction creates new branches. A single atom undergoing radioactive decay splits the universe into branches where it decayed and branches where it didn't. Multiply this by every atom in every star in every galaxy happening every instant, and the number of branches explodes beyond any hope of conceptualization. Consider your brain. It contains roughly 100 billion neurons, each with thousands of synapses. Neural activity involves countless quantum interactions, ion channels opening and closing, neurotransmitters binding to receptors, molecules changing state. Each of these interactions can go multiple ways. Your brain in any given second creates an astronomical number of branches, each corresponding to a slightly different pattern of neural activity, creating slightly different thoughts and decisions. The versions of you across these branches are mostly similar. They share your memories up to a moment ago, but they're diverging continuously, making different micro-decisions, having slightly different thoughts, moving along different trajectories through the space of possible experiences. The many worlds interpretation solves the measurement problem by denying that measurements are special. There's no collapse. The universe simply evolves according to the deterministic equations of quantum mechanics, creating a vast branching tree of parallel realities. It's an elegant solution in some ways, no need for mysterious collapses. No need to draw arbitrary lines between quantum and classical systems. Everything's quantum. Everything follows the same laws. The classical world we experience is just the appearance created by being embedded in one branch of the quantum multiverse. But it comes at a staggering ontological cost. The number of parallel worlds is not just large, it's unfathomably vast, probably infinite. Every quantum interaction creates new branches. A single atom undergoing radioactive decay splits the universe into branches where it decayed and branches where it didn't. Multiply this by every atom in every star in every galaxy, happening every instant, and the number of branches explodes beyond any hope of conceptualization. Where are these other branches? Not in space. They're parallel to our space, existing in a higher dimensional mathematical structure called Hilbert's space. Each branch is a complete three-dimensional universe, but they're separated in a different dimension that we cannot directly perceive. They're layered on top of each other, occupying the same spatial coordinates but in different quantum states, unable to interact because quantum decoherence keeps them apart. This is very different from the eternal inflation multiverse. Those other bubble universes are out there in space, separated by vast inflating distances. The many worlds universes are right here, overlapping with us, but in a different dimension of the quantum wave function. You can't travel to them by moving through space. They're not beyond any edge you could reach. They're orthogonal to space, existing in the structure of quantum reality itself. The philosophical implications are staggering. In some branches, you made different choices. In some branches, quantum fluctuations led to different histories. In some branches, events unfolded in ways that seem impossibly improbable from our perspective. But in the full many worlds multiverse, everything that can happen does happen, with frequencies determined by the quantum mechanical probabilities. Death takes on a different character in many worlds, at least in some interpretations. When you die in this branch, there could be other branches where you didn't, according to the theory. Some proponents have suggested that from your subjective perspective, you might only ever experience the branches where you survived, leading to a concept sometimes called quantum immortality. This idea sounds appealing until you consider the nature of those survival branches. Many of them would involve severe injuries or debilitation. The branches where you're healthy and alive would become progressively rarer as you age, but you might subjectively experience only those rare branches, never knowing how many versions of you have died along the way. Quantum immortality is controversial even among many worlds proponents. It relies on assumptions about the continuity of consciousness and subjective experience that may not hold, and many physicists argue it misapplies the theory. But it illustrates how radically many worlds, if correct, would change our picture of reality. You're not a single entity living a single life. You're a vast ensemble of versions, living out every possible history consistent with quantum mechanics, most of which will never be aware of each other's existence. Many worlds is not universally accepted. Some physicists reject it as metaphysical extravagance, arguing that postulating infinite unobservable universes to avoid a collapse mechanism is wasteful. Others embrace it as the most elegant and consistent interpretation of quantum mechanics. Surveys of physicists show varied results depending on when and how they're conducted, with some polls suggesting perhaps 15 to 20% favour many worlds, though these numbers vary considerably between different surveys, with the rest split among other interpretations or remaining agnostic. The question of whether many worlds is real touches on deep issues in the philosophy of science. What does it mean for a theory to be true if its predictions are unobservable? The other branches in many worlds cannot be directly observed or accessed. We can never visit a branch where we made different choices. We can never confirm that those branches exist. Does that make them unscientific? Or is it enough that many worlds is a consequence of taking quantum mechanics seriously, applying its equations consistently without adding extra assumptions? If many worlds is correct, then beyond the edge of our observable universe lies not just more space or other bubble universes. There's also an infinite forest of parallel realities, branching and splitting continuously, each one a complete cosmos unto itself, layered on top of and alongside our own in a higher dimensional space of quantum possibilities. These universes don't have edges in any spatial sense. They're separated not by distance but by decoherence, by the fundamental quantum separation that prevents different branches from interfering with each other. Is this what lies beyond? Parallel quantum realities? Or is the truth something else entirely? Perhaps the question itself is wrong. Perhaps beyond the edge is a meaningless phrase because the universe never began. Let's examine that possibility. We've talked about what lies beyond the edge of the universe in space, but there's another edge, one perhaps even more mysterious, the edge in time. The Big Bang, that moment 13.8 billion years ago when time began and space exploded into existence. Or did it? What came before the Big Bang? Can we even ask that question? The standard Big Bang model says no. Time itself began with the Big Bang. There was no before because time didn't exist yet. Asking what came before is like asking what's north of the North Pole. The question is meaningless because it assumes something the temporal dimension, extending past the beginning that doesn't exist in this framework. This answer has never satisfied everyone. It seems to beg the question, how can time just start? What triggered the Big Bang? Where did the initial conditions come from? Why did the universe begin in a particular state rather than some other state? These questions push at the boundaries of physics, and modern cosmology is beginning to offer answers, though they remain highly speculative. The problem with the Big Bang singularity is that it's a point where physics breaks down. If you extrapolate the expansion of the universe backward in time, general relativity predicts that all matter and energy was compressed into an infinitely dense, infinitely hot point at time zero, a singularity. But singularities in physics usually indicate that your theory is failing, not that the universe is actually infinite. General relativity is a classical theory. It doesn't include quantum mechanics. And at the extreme energies and densities near the Big Bang singularity, quantum effects become important. Particles and forces behave according to quantum rules, and spacetime itself might become quantum. The smooth, continuous spacetime of general relativity might break down into something discrete, grainy, fluctuating. To understand what really happened at the beginning, we need a theory of quantum gravity, a theory that combines general relativity and quantum mechanics into a single framework. Several candidate theories exist: string theory, loop quantum gravity, causal set theory, and others. These theories are incomplete and controversial, but they share a common prediction. The Big Bang singularity doesn't exist. The infinite density never occurs. Instead, something else happens, something that might allow time to extend before the Big Bang. One prominent idea is the Big Bounce. In loop quantum gravity, the equations predict that when matter compresses to extremely high densities, quantum effects create a repulsive force. Instead of collapsing to a singularity, the universe reaches a maximum density and then bounces back, expanding again. The Big Bang wasn't the beginning of time. It was the moment when a previous contracting phase transitioned to an expanding phase. Loop quantum gravity approaches this problem by treating spacetime itself as quantum. Just as matter is made of atoms, spacetime in this theoretical framework is made of discrete units, tiny loops of space connected to form a quantum geometry. These loops would have a minimum size around the Planck length. When you try to compress matter beyond a certain point in these models, you run into the granularity of space itself. You can't squeeze it any smaller because there's no smaller space to squeeze it into, according to this approach. This creates a natural maximum density, potentially preventing the infinite compression of a singularity. In models using loop quantum gravity, when a collapsing universe reaches the maximum density, quantum gravitational effects could become dominant. The attractive force of classical gravity might be overwhelmed by a quantum repulsion, a kind of a pressure that could arise from the quantum properties of geometry itself. The collapse could halt. The universe might rebound, transitioning from contraction to expansion. This is called the Big Bounce, and our Big Bang would be the moment of this transition, according to these speculative models. If this is correct, then before the Big Bang was another universe, one that was collapsing. That universe might have been expanding before its collapse, in which case it had its own Big Bang even earlier. You can push this back indefinitely in these theoretical models, creating a cyclic cosmology where universes expand, contract, bounce, and expand again in an eternal cycle. Each cycle might last hundreds of billions of years. Our current universe would be just one phase in an endless sequence, though this remains speculative and difficult to test observationally. What would this mean for the past? Time would extend infinitely far back in these scenarios, an endless sequence of cycles, each lasting perhaps 1 trillion years or more. Our universe, 13.8 billion years old, would be a relatively young phase in the current cycle. The previous cycle would have ended in a contraction that began hundreds of billions of years after that cycle's bounce. Before that was another cycle and another, stretching back without beginning in this framework. The total history of reality would be infinite, with no first moment, no ultimate origin. This sounds appealing in some ways. It eliminates the problem of the initial singularity by simply denying there was one. It provides a natural arrow of time within each cycle while making the universe eternal in the global sense. But it raises new questions. What happens to information during the bounce? If the universe contracts to near Planck density, quantum effects would scramble the structure of space and matter. The specifics of the previous cycle might be erased, leaving only generic initial conditions for the next cycle. Each cycle might be essentially independent, carrying little or no memory of what came before. Alternatively, the pre-bounce universe might have been very different from ours. Perhaps it had different physical laws determined by the specific way quantum gravity operates at maximum density. Perhaps information from the previous universe was mostly erased during the bounce, leaving only subtle traces we might never detect. Or perhaps the bounce creates new initial conditions each time, explaining why our universe has the properties it does not because of fine-tuning, but because of the dynamics of the bounce itself. Roger Penrose has proposed a different cyclic model called conformal cyclic cosmology. In his model, the universe goes through eons, with each eon ending in a state of maximum entropy, with all matter decayed into radiation. All black holes evaporated through Hawking radiation, everything reaching a uniform cold state. At this point, Penrose argues the distinction between a very large universe and a very small one becomes meaningless because there are no structures left to provide a sense of scale. This end state can mathematically connect to a new beginning, a new Big Bang, starting the next eon according to his framework. Each eon is infinitely long in one time coordinate but connects to the next eon through a conformal transformation, a mathematical rescaling of time and space that preserves certain geometric properties. This model remains speculative and is debated within the cosmology community. Another possibility comes from eternal inflation. We discussed how inflation creates a multiverse of bubble universes. But what started inflation in the first place? Some models suggest that inflation has no beginning. It's eternal not just into the future, but into the past as well. The inflating space has always existed, constantly creating new bubble universes, one of which is ours. This scenario eliminates the need for a beginning altogether. Time extends infinitely far back. There was no moment of creation, no initial state to explain. The universe or multiverse simply has always been, in an eternal state of inflation, producing pockets of normal space like ours throughout its infinite past and infinite future. But there's a complication with past eternal inflation. The Borde-Guth-Vilenkin theorem, proven in 2003, shows that any spacetime which has been expanding on average over its history cannot be extended infinitely far into the past without encountering some kind of boundary. At some point, there must be a boundary condition, a beginning of some kind. This doesn't necessarily mean a singularity. It could be a quantum state, or a different phase of space-time, or some kind of transition from a pre-inflationary era. But it suggests that even eternal inflation might not be truly eternal in both directions. There would need to be something before, some initial condition or state that gave rise to inflation, according to this mathematical result, though interpretations of what this means physically remain debate. Yet another approach comes from quantum cosmology, which tries to apply quantum mechanics to the universe as a whole. The Hartle-Hawking no-boundary proposal suggests that the universe doesn't have a beginning in the conventional sense. Instead, time becomes space-like near the Big Bang, forming a smooth surface with no boundary. Imagine the surface of a sphere. It's finite but has no edge. The North Pole doesn't have a boundary, it's just another point on the surface. Similarly, in this model, the Big Bang might be just another point in a four-dimensional spacetime, not a boundary or beginning. In this picture, asking what came before the Big Bang would be like asking what's north of the North Pole. The question assumes a structure, the extension of time past the Big Bang that doesn't exist in the model. Time simply curves around smoothly at the Big Bang, forming a closed surface with no edge or beginning according to this framework. The universe doesn't have a first moment. It has an earliest moment, the Big Bang, but that moment is not a boundary or singularity. It's just where time transitions from being time-like to being space-like, creating a smooth geometry with no sharp beginning. Stephen Hawking described this by saying that asking what came before the Big Bang is like asking what's south of the South Pole. The question is meaningless because it assumes time extends past a point where the geometry says it doesn't. Time, in the no-boundary proposal, is finite in extent but has no boundary, just as the surface of Earth is finite in area but has no edge. This remains a speculative theoretical model, not yet confirmed or refuted by observations. These ideas are speculative. We don't have a complete theory of quantum gravity, so we can't say with certainty what happened at the Planck scale, those first 10 to the power of negative 43 seconds of cosmic history. But the trend is clear. Modern physics is moving away from the idea of a singular beginning towards scenarios where the Big Bang is a transition, a bounce, or simply a particular point in an eternal structure. If there was a before, it might have been utterly unlike anything we know. The laws of physics might have been different. Time itself might have had a different character. Or perhaps there was no space at all, just a quantum state encoding possibilities that eventually gave rise to space-time. Some theories suggest the universe emerged from a quantum fluctuation in a pre-existing vacuum state, a universe-creating event triggered by the inherent randomness of quantum mechanics. The question what came before the Big Bang might not have a single answer. Perhaps different regions of the multiverse had different origins. Our bubble universe emerged from an inflating background, which itself might be eternal or might have bounced from an earlier state. Other bubbles might have different histories. The multiverse as a whole might be eternal, with no beginning or end, while individual pocket universes like ours have finite ages, measured from their particular moment of formation. This connects to the question of beyond the edge in space. If the multiverse is eternal in time and infinite in space, then the edge of our universe in either dimension is not an absolute boundary of existence. It's a local feature, meaningful to us but not fundamental to the cosmos as a whole. Beyond the edge in space are other regions of the multiverse. Beyond the edge in time are either earlier phases of a cyclic universe or an eternal inflating background from which we emerged. The universe, or multiverse, is both larger and older than we once imagined. Our observable bubble, 13.8 billion years old and 93 billion light-years across, sits within a reality that might extend infinitely far in space and infinitely far back in time. We occupy a tiny region of an eternal infinite cosmos, seeing only a minuscule fraction of what exists, and what exists beyond our horizons might be fundamentally unknowable, hidden behind barriers that no amount of technological progress can overcome. But there's one more possibility we should consider, one that takes the idea of beyond in a completely different direction. What if the dimensions beyond the three we perceive are not temporal or distant, but curled up at every point, hidden from view by their microscopic size? Let's explore that idea. You experience 3 dimensions of space: length, width, height. Every object you've ever seen, every place you've ever been, exists within this 3-dimensional arena. But what if there are more dimensions? Not far away, not in the distant future or deep past, but right here, curled up so small that you pass through them constantly without ever noticing? This is one of the central ideas of string theory, a proposed theory of quantum gravity that attempts to unify all forces and particles into a single framework. In string theory, the fundamental constituents of reality are not point particles, but tiny vibrating strings, loops of energy far smaller than any particle we've detected. Different vibration patterns of these strings correspond to different particles. An electron is a string vibrating one way, a photon is a string vibrating another way. But for the mathematics of string theory to work, spacetime cannot have just 4 dimensions, 3 of space and 1 of time. It must have 10 dimensions, or 11, depending on the specific version of the theory. Where are the extra 6 or 7 dimensions? The answer? They're curled up at every point in space, compactified into tiny shapes far smaller than any distance we can probe. Imagine a garden hose. From far away it looks one-dimensional a line, but zoom in and you see it has a circular cross-section. The hose is actually 2-dimensional. One dimension stretches along its length, and another dimension wraps around its circumference. If you were an ant walking on the hose, you could move forward and backward along the length, or you could walk around the circumference, eventually returning to your starting point. Now imagine that the circular dimension is much, much smaller. So small that even the ant can't perceive it. The ant would think it's living in a one-dimensional world, never suspecting the hidden circular dimension wrapped around every point along the line. This is analogous to our situation. We think we live in 3 dimensions, but there might be additional dimensions curled up at every point, too small to perceive. How small? Probably around the Planck length, approximately 10 to the power of negative 35 meters. This is far smaller than an atom, smaller than a proton, smaller than any distance we can currently probe. At every point in our 3-dimensional space, there might be a tiny 6-dimensional shape, a geometric structure called a Calabi-Yau manifold, wrapped up so tightly that it's invisible to us. What is a Calabi-Yau manifold? It's a specific type of 6-dimensional geometric shape that has special mathematical properties that some versions of string theory require. These shapes are named after mathematicians Eugenio Calabi and Xingtung Yau, who studied their properties. Calabi-Yau manifolds come in many varieties. Mathematicians have catalogued thousands of them, and the total number could be far larger, possibly millions or more, depending on how you count distinct shapes. Picture trying to visualize a 6-dimensional shape. You can't, not really. Our brains evolved to navigate 3-dimensional space. We can understand 2 dimensions easily, a flat surface. We live in 3 dimensions and intuitively grasp length, width, and height. But 6 dimensions, we can describe them mathematically, write equations that specify their properties, but we cannot visualize them in any direct sense. The best we can do is look at lower dimensional analogues or projections, shadows of these shapes cast into dimensions we can understand. The specific shape of these compactified dimensions determines the physics we observe. Different shapes give rise to different particles, different forces, different values for the physical constants. The enormous variety of possible Calabi-Yau manifolds, perhaps 10 to the power of 500 different shapes, corresponds to the landscape of possible low-energy physics in string theory. Each shape is a different vacuum of the theory, a different possible universe with different laws. Why do the extra dimensions compact in the first place? The mathematics of string theory allows for various compactifications, different ways the extra dimensions can curl up. Some compactifications are stable, meaning once the dimensions settle into that shape, they tend to stay there. The forces and fields in string theory could prefer certain configurations over others, and the universe might find these stable configurations. Our universe, according to string theory, could have settled into one particular compactification, one particular shape for the extra dimensions, producing the specific particles and forces we observe. However, why our specific compactification was chosen over others, if string theory is correct, remains an open question. If string theory is correct, then at every point in our 3-dimensional space, there are hidden dimensions extending in directions we cannot perceive. These dimensions aren't beyond the edge of the universe in the sense of being far away. They're orthogonal to the 3 spatial dimensions we know. Right where you're sitting now, there are 6 additional dimensions of space, curled up into a shape smaller than an atom. You're always in see them, moving through them, yet completely unaware of their existence. But these extra dimensions might not always be so small. In some versions of string theory, particularly those involving brains short for membranes, 1 or more extra dimensions could be much larger, even macroscopic. Our 3-dimensional universe might be a brain embedded in a higher dimensional bulk. Everything we experience, our particles, forces, light, is confined to the brain. We cannot move off it into the bulk. But gravity might be able to leak into the bulk, spreading into the extra dimensions. The word brain is short for membrane, generalized to various dimensions. A 1-dimensional brain is a string. A 2-dimensional brain is a membrane like a soap bubble surface. A 3-dimensional brain is the space we inhabit. These brains exist in a higher dimensional bulk, spaces of perhaps 10 or 11 dimensions total. The standard model particles, electrons, quarks, photons are confined to the brain, unable to leave. They can move through the 3 dimensions of the brain but cannot access the extra dimensions perpendicular to it. This could explain why gravity is so weak compared to other forces. Electromagnetism, for example, is vastly stronger than gravity. A tiny refrigerator magnet can lift a paperclip, overcoming the gravitational pull of the entire Earth. Why is gravity so feeble? Perhaps because it dilutes into extra dimensions. While electromagnetic force is confined to our 3-dimensional brain, gravity spreads into the higher dimensional bulk, weakening as it does so. The graviton, the hypothetical particle that mediates gravity, can leave the brain and explore the extra dimensions, while photons and other particles cannot. If this is true, then the universe has edges we haven't discussed. Our three-dimensional brain might have boundaries in the extra dimensions. Beyond those boundaries lies the bulk, a higher dimensional space we cannot access, but which exists nevertheless. Other brains might exist in the bulk parallel to ours, perhaps only a fraction of a millimeter away in the extra dimension, but utterly inaccessible to us because we're trapped on our brain. Imagine two sheets of paper lying on a table, separated by a millimeter. To a two-dimensional being living on one sheet, the other sheet is right next to them in the third dimension. But the being cannot perceive or access that third dimension. It's trapped on its sheet. The other sheet might as well be infinitely far away, despite being only a millimeter distant in a direction the being cannot even conceive of. This is our situation with respect to other brains in the bulk. They could be extraordinarily close in the extra dimensions, yet completely unreachable. These parallel brains could be entire universes. They would be right next to us in the extra dimension, closer than the nearest star in our own three-dimensional space, yet we could never visit them. We're three-dimensional beings, plus one time dimension, living on a three-dimensional surface, the brain, unable to perceive or access the higher dimensional bulk in which our brain is embedded. It's like asking a character drawn on a piece of paper to step off the paper into the three-dimensional room. The character is confined to the paper. It cannot leave. It might not even be able to conceive of the third dimension perpendicular to its flat world. Some versions of brain cosmology suggest that the Big Bang could have been the result of a collision between brains. Two parallel brains, drifting through the bulk, crashed into each other. The enormous energy of the collision could have created the hot, dense state we call the Big Bang. This scenario would eliminate the need for a singularity in these models. The Big Bang becomes a high-energy event, but not an infinitely dense one, and it suggests that such collisions might happen repeatedly, creating a cyclic cosmology where our universe experiences periodic Big Bangs as our brain collides with others in the bulk. The ekpyrotic model, developed by physicists including Paul Steinhardt, proposes exactly this kind of scenario. Two brains approach each other through the bulk, collide, bounce apart, and eventually approach again. Each collision creates a big Big Bang in each brain. The cycle repeats eternally in this framework. In this model, the universe before the Big Bang was a brain approaching ours, and the Big Bang was their collision. Eventually, the brains would separate, slow down, and begin approaching again, leading to another collision billions or trillions of years in the future. This remains a speculative model with various technical challenges that researchers continue to work on. What would it be like in the bulk? We can only speculate. The extra dimensions might be curled up like the other six, or they might be large or even infinite. The bulk might contain exotic forms of energy and matter that we cannot detect from our brain. The gravitational effects we attribute to dark matter might actually be gravitational influences from objects in the bulk, masses living in the extra dimensions that we can't see but whose gravity affects us. Some theories propose that dark matter is ordinary matter living on a parallel brain, pulling on us gravitationally through the bulk. The idea of extra dimensions offers yet another answer to what lies beyond the edge. Not just more of our three-dimensional space, and not just other bubble universes or quantum branches, but entirely new dimensions of space perpendicular to everything we know. These dimensions might be tiny and curled up, or they might be large. They might contain other brains, other universes, other realities, and we might be forever confined to our three-dimensional slice, unable to even point in the direction of these extra dimensions, let alone explore them. String theory remains unproven. We have no direct evidence for extra dimensions, no experimental confirmation that strings are the fundamental building blocks of reality. The theory is mathematically elegant and has produced deep insights, but it has also been criticized for making few testable predictions and for the proliferation of possibilities in the landscape. Some physicists embrace string theory as our best hope for a theory of quantum gravity. Others dismiss it as an untestable mathematical exercise disconnected from real physics. But if string theory is correct, then reality has more dimensions than we perceive, and beyond the edge might mean something we never anticipated, not further away in the dimensions we know, but perpendicular to them, in dimensions we can neither see nor visit nor even properly imagine. We've explored several possibilities for what lies beyond the edge of the universe. More space extending infinitely, other bubble universes, separated by eternally inflating regions, quantum branches layered on top of our reality, a previous universe before the Big Bang or no beginning at all, extra dimensions, curled up or extended, and each scenario transforms our understanding of edge and beyond. But there's one more possibility we should consider, perhaps the most unsettling of all. What if the entire universe, everything you've ever experienced, every galaxy and star and planet, is not fundamentally real? What if it's all a simulation, a computer program running on hardware in some higher level of reality? What if the edge of the universe is the edge of the simulation, the point where the programmers decided to stop computing? This is the simulation hypothesis, and while it sounds like science fiction, it's been seriously considered by philosophers and physicists alike. The argument, most famously articulated by philosopher Nick Bostrom, goes something like this. If it's possible to create simulated universes that are sophisticated enough to contain conscious beings, and if civilizations that reach such capabilities tend to create many such simulations, then such simulations could vastly outnumber the one real universe. Therefore, any given conscious being might be statistically more likely to be in a simulation than in the base reality. This is a philosophical argument, not a scientific claim, and it rests on several assumptions that may or may not hold. Think about video games and computer simulations we create today. They're at a primitive compared to reality, but they're improving rapidly. In a few decades or centuries, we might create simulations detailed enough that the simulated beings inside them become conscious, capable of wondering about their own reality. Those simulated beings might develop science and technology and eventually create their own simulations nested within the first. If this is possible, then there could be many, many layers of simulation, each one creating new simulations inside itself. At the bottom is base reality, the one true universe. Above it are countless layers of simulated universes. If you're a conscious being, what's the probability you're in base reality versus one of the countless simulations? The odds favour simulation. This argument has been discussed by philosophers like Nick Bostrom and has captured public imagination. But what does it imply about the edge of the universe? If we're in a simulation, then the universe might have limits imposed by computational resources. The simulators might not bother simulating regions of space that no observers will ever visit. The edge of the observable universe might be the edge of what's actually being computed. Beyond it, nothing, or rather, no computation until an observer heads in that direction, at which point the simulation generates new content as needed. This would explain certain strange features of quantum mechanics, like the fact that particles don't have definite properties until measured. Maybe it's they're not computed until someone looks. The simulation saves computational resources by rendering only what's necessary, like how video games only render the parts of the world visible to the player. This is speculation, of course, and represents one way to interpret quantum behavior, not an established explanation. Of course, this hypothesis is unfalsifiable. Any evidence you might gather is part of the simulation. Any physical law you discover is a law programmed into the simulation. You can't step outside it to check. Some philosophers argue this makes the simulation hypothesis meaningless or unscientific. Others counter that it's a genuine metaphysical possibility we should take seriously. If we're in a simulation, then beyond the edge of the universe lies not more universe, but the hardware and software of the simulation itself. A reality that might be incomprehensible to us, operating on principles utterly unlike the physics we know. The simulators might be entities we can't understand in a universe with different laws, running our universe as a curiosity, an experiment, or a game. Or perhaps the simulation hypothesis is wrong. Perhaps we do live in base reality, and the universe we observe is the genuine article, not a computed approximation. But even entertaining the possibility reminds us how little we truly know. Our observations are limited to our cosmic bubble. Our theories extend beyond observation but remain speculative. We can't be certain about the true nature of reality, the ultimate structure of the cosmos, or what lies beyond the boundaries of what we can ever hope to see. We've journeyed through cosmology's most profound questions, examining what might lie beyond the edge of our observable universe. The answers we've encountered are not simple or comforting. They challenge our intuitions, stretch our imagination, and push at the limits of what science can address. Let's summarize what we've learned. First, there's the straightforward possibility. Beyond the edge of our observable universe lies simply more universe. If space is flat and infinite, Then there are more galaxies, more stars, more planets, extending forever in all directions. The observable universe is a finite bubble in an infinite cosmos. Travel in any direction for long enough and you'd never reach an edge, because there is no edge to reach. And in an infinite universe, every possible arrangement of matter repeats infinitely many times, meaning there are countless duplicates of you, living out every possible variation of your life. Second, there's the eternal inflation multiverse. Our observable universe is one bubble in a vast sea of inflating space. Other bubbles form constantly, each one a separate universe with potentially different physical laws. These bubble universes are separated by regions of space expanding so rapidly that no signal can ever cross between them. The multiverse is eternal, constantly creating new universes, and each one is causally disconnected from all the others. Third, there's the quantum multiverse. If the many worlds interpretation is correct, then every quantum interaction creates branching realities. These parallel worlds are not out there in space, they're layered on top of our universe in the quantum wave function, separated by decoherence rather than distance. Every possible history compatible with quantum mechanics is real, unfolding in some branch of the infinite quantum tree. Fourth, there's the possibility that beyond extends in time as well as space. Perhaps there was no Big Bang singularity, but instead a big bounce from a previous universe. Or perhaps time extends infinitely far back, with no beginning at all. The edge in time might be an illusion created by our limited understanding of quantum gravity. Fifth, there are extra dimensions curled up at every point or extending in directions we cannot perceive. Our three-dimensional universe might be a brain in a higher dimensional bulk, surrounded by other brains we can never access. The edge might not be a location in our familiar dimensions, but a boundary in dimensions we don't even know exist. And finally, there's the unsettling possibility that the universe is a simulation, and the edge is simply where the computation stops. Beyond lies not more universe, but the hardware running the simulation, a meta-reality we can never access or understand. Which of these scenarios is correct? We don't know. We might never know. The observable universe is all we have direct access to. Everything beyond our cosmic horizon is inference, extrapolation, speculation grounded in theory, but not confirmed by observation. Different physicists favor different scenarios. Some embrace the eternal inflation multiverse as the natural consequence of cosmic inflation. Others prefer the quantum multiverse as the simplest interpretation of quantum mechanics. Still others hold out hope that future theories will eliminate the need for any multiverse at all. What we can say with confidence is this: the universe is vastly larger and stranger than we once imagined. The stars and galaxies we see are just a tiny sample of what exists. Most of reality lies beyond our cosmic horizon, hidden by the finite speed of light and the expansion of space. Whether what lies beyond is more of the same, or other universes, or parallel quantum realities, or higher dimensions, or something else entirely, we cannot be certain. This realization is both humbling and awe-inspiring. Humbling because it reveals the limits of human knowledge. No matter how powerful our telescopes become, no matter how sophisticated our theories grow, we will always be confined to our cosmic bubble. There are questions we cannot answer by observation, truths about the universe that might be forever hidden from us. Yet this limitation doesn't make the questions meaningless. Some philosophers argue that if something is forever unobservable, it's not part of science. Science deals with testable predictions, observable phenomena. Theories that make no testable predictions aren't science, but metaphysics. By this standard, much of what we've discussed, the multiverse, many worlds, extra dimensions, pre-Big Bang cosmology, falls outside science's domain. These ideas make few or no predictions we can test with current or foreseeable technology, but other philosophers and physicists disagree. They argue that these theories are natural extensions of well-tested physics. Eternal inflation follows from cosmic inflation, which we have good evidence for. Many worlds follows from taking quantum mechanics seriously, applying it consistently without adding arbitrary collapse mechanisms. Extra dimensions follow from string theory, which offers hope of unifying all forces. These theories might not make direct predictions about unobservable regions, but they make predictions about observable features that constrain what the unobservable regions are like. Consider an analogy. You're in a house, but you can only see one room. The doors are locked, the windows painted over. You can never leave this room or see outside it. Can you still do science? Can you theorize about what the rest of this house is like? Absolutely. You notice air currents, suggesting there are other rooms connected by ventilation. You hear sounds, indicating other spaces beyond the walls. You measure the room's temperature and humidity, which depend on the house's overall structure. You use all this information to build a model of the house, even though you can't directly observe most of it. That's our situation with the universe. We're trapped in our observable room, our cosmic bubble. But we can detect subtle effects that hint at what lies beyond. The uniformity of the cosmos suggests it extends far past what we can see, probably with the same properties. The mathematical consistency of our theories suggests they apply beyond our horizon. The laws of physics we discover here probably apply everywhere, allowing us to extrapolate beyond observation. But it's also awe-inspiring because it shows how ambitious human curiosity is. We're not satisfied with observing the stars and planets we can see, and we want to know what lies beyond. We construct mathematical theories that extend past our cosmic horizon, so making predictions about things we can never directly observe. We contemplate multiverses, extra dimensions, quantum branches, and simulated realities. We push our understanding to the absolute limits of what physics allows. Think about what this represents. We're primates who evolved on an African savanna, developing brains to navigate social hierarchies and hunt game and gather plants. Those brains weren't designed to understand quantum mechanics or cosmic inflation or higher dimensional geometry. Yet we've taken these savanna-optimized brains and used them to probe the deepest secrets of reality. We've discovered that space and time are unified, that the universe is expanding, that matter is made of quantum fields, that reality might have more dimensions than we can perceive. This is extraordinary. It speaks to something profound about the relationship between mind and cosmos, about the power of mathematics to describe reality, about the possibility that the universe is comprehensible despite having no obligation to be. The physicist Eugene Wigner once wrote about the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical patterns correspond so precisely to physical reality? Why should equations written on paper describe the behavior of galaxies and atoms? There's no obvious reason this should be true. Mathematics could have been just a game we play, disconnected from physics, but it's not. Mathematics describes reality with stunning accuracy. This suggests something deep about the nature of reality itself, though what exactly that something is remains mysterious. The edge of the universe, in all its forms, represents the boundary of human knowledge. But it's not a wall we've given up trying to scale. It's a frontier that inspires us to develop better theories, conduct more sensitive experiments, and ask deeper questions. Every advance in cosmology pushes our understanding a bit further, reveals new mysteries, and reminds us how much we have yet to learn. Perhaps future generations will confirm the existence of a multiverse, or discover evidence of extra dimensions, or develop a theory of quantum gravity that reveals what lies beyond the Big Bang. Or perhaps some questions will remain forever unanswered, mysteries that are in principle beyond the reach of science. We don't know which is the case, but the attempt to find out what drives us to build bigger telescopes, to probe deeper into the early universe, and develop theories that unify our understanding of nature is itself a profound expression of what it means to be human. Consider what we've learned in just the past century. In 1920, we thought the Milky Way was the entire universe. We didn't know about other galaxies. We didn't know the universe was expanding. We had no conception of the Big Bang, no understanding of quantum mechanics or general relativity in any practical sense. The observable universe, as we understood it then, was millions of times smaller than we now know it to be. In just 100 years, we've expanded our cosmic horizons by incomprehensible factors. We've discovered dark matter and dark energy, exotic components that make up 95% of the universe's contents. We've detected gravitational waves, ripples in space-time itself. We've found thousands of planets around other stars, transforming exoplanets from speculation to observational fact. We've mapped the cosmic microwave background, captured light from the universe's infancy. We've watched galaxies as they appeared mere hundreds of millions of years after the Big Bang, using telescopes that are marvels of engineering. What will the next century bring? What will cosmologists in 2025 know that we don't? Perhaps they'll have confirmed or refuted string theory. Perhaps they'll have detected signatures of extra dimensions, or found evidence of the multiverse, or made observations that force a complete revision of cosmology. Or perhaps they'll have reached hard limits, confirming that some questions can never be answered, that the universe keeps some secrets forever. We stand at the shore of the cosmic ocean, looking out at a horizon we can never cross. Beyond that horizon lies the vast majority of existence, whatever form it takes. More universe, or other universes, or quantum realities, or dimensions we cannot perceive. We'll never visit those regions. We'll never see what's there directly, but we can wonder. We can theorize. We can use mathematics and physics to extend our understanding beyond what observation alone can reach. And in doing so, we push back against the limits of knowledge, claiming intellectual territory even in regions we can never physically explore. The edge of the universe is the edge of everything we can know, but it's not the edge of our curiosity, our imagination, or our determination to understand, and perhaps that's the most important discovery of all. Not what lies beyond the edge, but the fact that we care enough to ask. The night sky has never looked the same once you understand what you're really seeing. Those stars are not distant points of light in a cosmic ceiling. They're suns, separated by voids so vast that light takes years to cross them. The galaxies are collections of hundreds of billions of such suns, and the ones we see are just the ones close enough for their light to have reached us. Beyond them, in the darkness, are trillions more galaxies we can see, and beyond those, potentially infinitely many more we cannot. You are an observer standing inside a bubble of visibility, watching an ancient light show performed by objects that might no longer exist in the form you're seeing them. And beyond the edge of what you can see lies most of existence, forever hidden behind horizons imposed by physics itself. That's the universe we live in, vast beyond measure, largely unobservable, possibly infinite, definitely stranger than we ever suspected. Every photon that reaches your eye from a distant galaxy has travelled for millions or billions of years, surviving its journey through the expanding cosmos. That galaxy, when it emitted the photon you're now seeing, was young, different, perhaps filled with stars and structures that have long since evolved or died. You're not seeing the galaxy as it is. You're seeing it as it was. The further away you look, the further back in time you see. The deepest images from the James Webb Space Telescope show galaxies as they appeared more than 13 billion years ago, less than a billion years after the Big Bang. Those galaxies, if they still exist, are now ancient. Their early structures evolved into spirals or ellipticals or merged into larger systems. But we see them frozen in time, eternal in the ancient light that finally reached us after kinds of travel. This creates a strange situation. The universe has an age and a history, but different parts of it are visible to us at different stages of their history. We can't see the present state of distant objects. We can only see their past. The universe we observe is not a snapshot of a single moment. It's a view through time, with nearby objects seen as they recently were, and distant objects seen as they anciently were. The cosmos is like a vast museum of its own history, with each distance representing a different era, and maybe, just maybe, that's how it should be. A universe small enough to fully explore, simple enough to completely understand, would be a disappointment. The fact that the cosmos extends beyond our grasp, that it hides secrets we may never uncover, that it poses questions we might never answer, these things give us something to reach for, something to wonder about, something to remind us that for all our knowledge and technology, we remain small creatures in an incomprehensibly large reality. Throughout human history, we've pushed at boundaries. We explored the Earth, mapping every continent and ocean. We reached into space, sending probes to other planets and telescopes to orbit above our atmosphere. We've peered into atoms, discovering quarks and electrons and the fundamental forces. We've looked back in time, observing light from the infant universe. At each stage, we've encountered new horizons, new mysteries, new questions that demand answers. The edge of the universe is the latest in this long sequence of boundaries. And like all the previous boundaries, it's not a barrier, but an invitation to understand more deeply. So when you look up at the night sky, remember, you're seeing a tiny fraction of what exists. Beyond the visible stars are more stars. Beyond those are galaxies upon galaxies. Beyond the edge of observation might be infinite space, or other universes, or quantum branches, or dimensions we can't perceive. We don't know, we might never ever know, but we'll keep looking, keep asking, keep pushing at the boundaries of understanding. Because that's what we do. That's what makes us human. We stand at the edge of the known and peer into the unknown, not content with ignorance, not satisfied with easy answers, always reaching for that next piece of understanding that will push back the darkness just a little bit further. The universe doesn't end at the edge of what we can see, it begins there. It begins in the questions we ask, the theories we build, the observations we make, the wonder we feel when confronting the vastness and strangeness of reality. The edge is not a wall, it's a horizon, always receding, always inviting us forward, always promising that there's more to discover, more to understand, more to know. And in that endless vasting toward horizons we can never fully grasp, in that eternal quest to understand what lies beyond our current knowledge, we find something profound, not just facts about the universe, but meaning in the search itself. The journey towards the understanding, even if the destination remains forever beyond reach, gives purpose to our brief moment of consciousness in this ancient, expanding cosmos. We are the universe looking at itself, trying to understand its own nature. For 13.8 billion years, matter and energy flowed and evolved and organized, creating stars and planets and ultimately life and consciousness. And now, on at least one small planet orbiting an ordinary star in an ordinary galaxy, some of that matter has arranged itself into brains capable of contemplating the cosmos itself, capable of asking about edges and horizons and what lies beyond, capable of wonder. That's what's truly extraordinary. Not just what lies beyond the edge of the universe, but the fact that there are beings like us, made of stardust, capable of asking the question. The universe has spent billions of years creating observers, entities capable of looking out into the darkness and asking what's there, and then working step by step, observation by observation, to find answers. We may never know everything about what lies beyond our cosmic horizon. The universe may keep its ultimate secrets forever, but the quest to understand, the drive to push past our limits, the refusal to accept we can't know as a final answer, these define us as much as anything. We are explorers by nature, boundary pushers, question askers, mystery solvers. And the universe, vast and strange and full of wonders, gives us an infinity of mysteries to explore. The edge of the universe is not an ending, it's a beginning. The beginning of imagination, of theory, of mathematical exploration into territories no eye can see. The beginning of philosophy, as we contemplate existence and the meaning in a cosmos that might be infinite. The beginning of humility, as we recognize how small our observable bubble is compared to the enormity beyond. And the beginning of wonder, as we stand in awe of a reality far stranger and grander than our ancestors ever dreamed. If you enjoyed this exploration into the deepest mysteries of cosmology, hit that like button and subscribe to the channel. There's so much more to discover about our strange and beautiful cosmos, and we'll be diving into all of it together. The universe is vast, the questions are profound, and the journey to understanding never ends. Let's keep exploring together.